So I looked at the Math IS. There was widespread success. Most people got on, was able to do it. If you still couldn't log on, there's a few people that were having log-on difficulties. Just talk to me after class. We'll get it straightened out. But it seems like overall, everyone or most people were able to get to the homework and do at least most of it. All right, so look, this afternoon I'll put the next Math IS assignment up. Just pay attention to Canvas or go to Math IS, look on the calendar. Sometime later this afternoon, the next one will be up on what we're doing now, which has to do with area. So this is where we left off last time. We were looking at this function f, and then looking at sweeping out area between f and the x-axis. And we had this associated function, capital F, was the integral from 1 to x of f of t dt. So your first task, talk to the person next to you. I want to complete an exact definition, so all the details and precise definition for what exactly is function f. So the meaning of it, right? So what does it do? What is it about? So yes, it's the integral from 1 to x f of t dt. But so what, right? So what? What does it do? What is its function? All the details and exact, precise definition. So get a partner, talk that through, and I'll start attendance. Go. What is capital F function? Basil. Carla. Cameron Baca. Micah. Damien. Chance. Jordan. Deanna. Jojo. Bangchen. Lee. Hannah. Griffin. Sophia. Ray. Ray Elementi. Ray. Jasper. Jesse. Okay, here we go. Jesse, you're up. What did you talk about here? So what the function capital F is, what kind of function, what does it do, all the details.
So the small f of x is the rate of change.
Okay, rate of change of what?
The rate of change of the actual graph.
So small f is the rate of change of small f?
No, f of x, the small f of x is the actual graph that is on the graph.
Right.
And the big f of x is finding the actual value from 1 to x.
Okay. So of what though? So what is it? Well, capital F is what kind of function, and specifically what quantity is it related to? Yeah. Yes, Deanna.
So do you the exact net accumulation of the sign?
Okay, exact. Is it exact net accumulation? Yeah. Exact because it's what? Integral. Net accumulation because it's an integral, right? So that's what integrals give us. They give us exact net accumulation. And you said of what? Of the signed area. And specifically, what signed area is it?
From 1 to x. Or no.
Yeah, that's true. That's true. So like horizontally, it's from 1 to x. But what about what gives us the area up and down, right? So yes, it's from 1 to x, and it's also, yeah.
Under the curve.
Yeah, so between, so not always under, right? So not always under. So between the curve and the x-axis, right? So we'll say signed area between from x equals 1 to x. So yeah, so function f is the exact net accumulation of signed area between the curve and the x-axis from x equals 1 to x. Okay, what was the signed area? What was that about? So what is signed area? Isn't it just area? Yeah.
It is signed that the rate can also be negative.
Right, so if signed area means if you just take the function as it is, whenever that function is negative, then the rate is negative. And what happens to the capital F function? What happens to the exact net accumulation when the rate is negative? What's that? Yeah, it decreases, right? So if it was an area function, what would happen? If it was an area function. What would happen with the net accumulation of area? It would go up and up and up and up, no matter where the area was, right? Because area is always positive. But we're calling this signed area because when that function dips below and those values are negative, well, then the rate is negative and our accumulation goes down, right? So whenever f is above the x-axis, accumulation of signed area goes up. And for x values where f is below the x-axis or f is negative, little f is negative, then the accumulation decreases. So it's not really area, it's kind of like difference of areas, kind of, okay? So now I have another task for you here. So here's two mystery functions, capital P and capital Q, and they are coordinated with the animation, all right? So you're going to look at what the values of P or Q are doing, and you're going to do two things. First, you're going to identify what is the value capital P, or what is the function capital P, and what is the function capital Q relative to what's happening in the animation. And then the second task is write a true mathematical statement that brings P and Q together. So the function P, what did you say the function P was relative to this animation here?
We said P was the y value.
Y value of?
The y value of the function.
Just the function little f?
Yes, little f.
Yeah, so capital P is the y value of the function little f. Agree?
Yeah.
So therefore, capital P is what function? Little f, right? If it's the y values, that's what little f is, the y values of the graph. So P is the y values. Okay, Q, what is Q? Yes, sir?
Q would be the exact net accumulation of P of n, or it would be the integral from 1 to x of P of n. Or
So is it the accumulation of the function, P? So everything's correct, but it's
the signed area.
Yeah, right. Signed area, right? What? Is that? That's two different things. That's two different things. Yeah. So to say that it's the accumulation of the function is not correct because we're talking about something else besides the function. It's the accumulation of signed area. Okay, those are two different things. So I'm not just like being picky. Okay. All right. So therefore, if I wanted to write a statement that brought them together, what happened to my? I guess I never had it. If I want to write a statement that brings P and Q together, what would I write? Somebody new. What would I write? Yes, sir.
Q of n equals the integral from 1 to n
No.
P of x dx.
So Q of n is the particular value as n increases. So to make it a function, we really just want Q of, because Q of n is kind of like one value of the function.
Q of x.
Q of x, okay, you said Q of x equals?
The integral from 1 to n of P of x dx.
Okay, 1 to x of,
Q of n dn.
yeah, you could do P of n dn, that's okay. Normally we use t to represent all those values, but P of n dn would be okay. And it's just what the slider is called in GC there. Okay, so this is, yeah, because if this is our function, we know that the function values, the y values, are the rate of change of signed area. Q was giving those values of signed area. So basically Q was what we called capital F before, right? And P was what we called little f. So I just wanted to see if you could recognize that by the numbers. Okay, so another exercise like this. Any questions on that? Okay, another exercise like this. So we said capital P and capital F are the same, so there they are. So now I got two new functions, G and H. So as you watch the values of G and H, identify what those are, and then write mathematical expressions for each of those. Write a mathematical expression that involves G, and write a mathematical expression or statement that involves H. So now it's not reading anything, right? So there's nothing going on with G until now it starts giving values. And so looking at those values of G, what is G? So is it area, first of all?
No.
Because? So G's kind of kicks in right there, and then -1, -2, -3, -4, -5, -6. What is G? Is it area? Why can't it be area?
Area is always positive, so
It's negative. All the values are negative, okay?
Can it be signed area?
Can it be signed area? Sure, it can be signed area. Signed area can be negative. So is it the signed area? Okay, but the signed area, but what's different? It's not starting at 1, it's starting at 2. So if we wanted to write the expression, this is the exact net accumulation of signed area. So I'm going to write, what do I write? Integral from? Starting from 2 now, right? Of what? Yeah, I could use little f or I could use p, right? P and f are the same function. How many people got that before we started discussing it? Did anyone get it? Do you see why this is right? So, because it's starting to accumulate, but negative, starting at 2. But if you look at it, so it's accumulating area, but the opposite of area. So therefore, it's signed area, which is going to just get bigger and bigger negative the whole way because our rate is negative the whole time. So it's just going to keep getting larger and larger negative. Question?
But for the g of x function, then what if you put like a 1? Because if x equals 1, then you get a value.
Right, you would.
But it just says there's no value before 2.
Right, because then that if I had put values in there before the 2, then this would have been hard to get. Hard to.
Do you just signify the domain somehow then?
What's that?
You just signify that the domain is not.
Sure. How about that? Yeah, so for the point of the exercise, if I had values that were less than 2, it would have been harder. So my real goal was for you all to see and come up with this. Okay, questions? Does it make sense? So signed area, if your function is always negative, then it's just going to get larger and larger negative. Like the opposite of the area, right? This would be the opposite of the area. Okay, what about H? What about H? So let's see what that looks like. What'd you notice about H? Yeah.
It would be the area from 1 to 2
Yeah.
minus the area from 2 to 3 or plus the absolute value of the area from 2 to 3. So we would have the h of x equal the integral from 1 to 2 of f of t dt minus the integral from 2 to x of f of t dt.
Okay. All right. But all right. So you're talking about how to write the function h. So just can we just concisely say what it is? Yeah.
Is this area not side area?
Okay, is it area and not signed area, she said. Is that what it is? Yeah, so this is, when you get to 2 now, instead of starting to decrease, it just keeps going up. So that means that this is a true area function, right? So it's like 1, now it's 1, 2, 3, so it keeps going up and up and up. And even when we pass 2 and it goes underneath, the value keeps increasing, 4, 5, 6, etc. So this is a true area function, or net accumulation of area. And so we'll say, so this is area or unsigned area. Those mean the same thing. Unsigned means always positive. Area is always positive. Okay, so writing an actual area function takes a little more work, right? So the unsigned area is simple because it's just the integral of the function, right? Because that function is the rate, but it's the rate of signed area. It can be positive or negative. It can increase or decrease. Now if we want to write a true area function, it actually takes a little more work. So I want to write the true area function. How can I do that? What do I need to change about this? So first of all, starting from where? H starts from where? Back from 1 again, right? Up until x, right? So of what? How am I going to get a true area function, Dylan?
The absolute value of ft.
And someone had, is that what you're going to say? Yeah, so now if I just take my function f and force it to always be positive, that's what absolute value does, right? Won't that do it? Will that give me the function h? Yeah, because now when f is positive, we get exactly what we had before, but when f is negative here in the gray part, it's going to make all those function values positive, and then it'll keep increasing. This h, capital H, will keep increasing even when little f is negative. So it'll truly track area, accumulated area. Does it make sense? Okay, so now what I want to do is I want to write capital H without absolute value. This is a good exercise. I want to rewrite capital H, but I don't want to use absolute value to do it. So what will that entail? So what will the structure of my overall H function be if I'm not allowed to use absolute value anymore? How would I be able to do that? Any ideas? What's that? Yeah, so I can't, I don't want to use absolute value at all. So, any idea? Yes, sir?
Didn't that guy say it earlier? Like how you split up the integral?
Okay, split it up, is that what you're going to say? Yeah, so we're going to have to split it up because the little f function, if we don't have absolute value, the little f function can't get us area because it'll dip negative. So we're going to have to split this thing up. So let's do it. And so we're going to do what's called a piecewise function. Remember those? Piecewise function. It means you have a certain rule for certain x values and a different rule for other x values. Okay? So what's my first set of x values that have all the same rule? So for what x values will I have my first rule of the function? Yeah, 1 to 2. So 1 including 1. And then we want to actually include 2 as well. And then my next rule will be from? So the animation stops at 3, so we'll say 2 to 3. Now here, I included 2 in the first line for this rule, so I don't want to include it here, right? So it's going to be up to 2 and including 2 here, and then just after 2, up to 3 in the second line. Okay, so here's the trick to this. So the first part is hopefully pretty simple. Hopefully most of us can get that first part. Second part, I want to make sure that when I plug an x value in between 2 and 3, I'm going to get all of the accumulated area since 2. So that's the trick to this. if I put in 2.7, I want to get all the accumulated area from 1 to 2.7. So this is the slightly more challenging part, and keep that in mind. Any x value between 2 and 3 needs to take into account all this previous area and then all the accumulated area up to x in the second part from 2 to 3. Yeah?
From 1 to x,
Okay?
and then I did f of n and
Yeah, and f of n dn is fine, but I'll just stick with f of t dt. How do you do? Does it work? Is it right? Yeah, hey, it's just going to be the accumulation. It's already area because f is always positive in this region, so we can just use this unsigned area. It's fine. That's the unsigned area, but it'll be positive because f is always positive there. Okay? Let's see who the lucky one is here. A random number generator. Number 6. Damien. Where's Damien? Okay, you're up. So how'd you do on part 2? What were their ideas about that? Integral from 2 to x? Okay. Like that? So is that going to get me area? Is that going to, from 2 to x f of t dt, is that going to get me area? So what will it get me? Remember, so this was, what will the values of this function be? They're going to be negative because the rate is negative. So how can I make that area? What's that? Yeah, so let's make it negative, right? So yeah, so if I make the if I take the opposite of the rate, then that'll do it. Or that negative can be out in front of the integral. Doesn't matter, either way. So you put the integral out in front of the negative out in front, or the negative inside. Does this get me all the area from 1 up to x in the second thing? Does it get all of it? What area does it get me? Just in the gray area. So what do I need to? Yeah, is it Elizabeth? Was it? Emily, sorry. Got the E.
So if I was gonna go back to like the first function that you said was big F or something,
Yeah?
I would say big F of 2 minus the integral that you have there.
Okay. So and then what does that big F of 2 represent? What is that? Why do you want to put that on there? What is it?
Because that would be the net accumulation of the signed area from you get into 2 or 1 to 2, right?
Right. So what we've left off here, you're saying what we've left off here is the green area. So rather than using capital F, what can I use? What is all the area, according to this, what is all the area up from 1 to 2? Okay, the first piece, but at a particular value, right? At 2. So how can I represent that? You guys are becoming experts at function notation, right? What could I write? H of 2. H of 2 is all of the accumulated area up to 2, right? So it's, if I were to put 2 in for x, it would take me to this front one, and we would do the integral from 1 to 2, f of t dt, and that's h of 2. So I could also write here, this could also be, you could have wrote the integral from 1 to 2, f of t dt. That's what h of 2 is, right? Because it's defined right there, when x is 2. And what is that? That's all the accumulated area, all the green area, all the accumulated area from 1 to 2, plus what? The opposite of the accumulated signed area in the second part to make it positive. So yeah, so you could have a minus there. You could just do minus the integral. That'd be fine too. Does this make sense? Okay, what does that kind of look like? Notice anything? You recognize that? Yeah, this is like total accumulation, right? So part of this net accumulation function, capital H, the second part is a lot like a total accumulation function. Everything from before, right? All the accumulated amount from before, plus the new accumulated amount in the current part. Yeah. So this is kind of like a total accumulation function as part of a net accumulation function. right, so now I want you to write. Noticing what the function does here after 3. So here's x greater than 3. I want you to write the next piece. What would the next piece be? Go. Alexander. Where's Alexander Roth? Where are you? There you are. Okay, did you get it?
Would be h2 plus h4 plus the integral from, what is that, 3? Integral from 3 to x of f t dt.
Okay, h of 2 plus h of 4. So we don't have an h of 4 yet because x equals,
H of 3.
so h of 2 plus h of 3.
Yeah.
Okay, then plus.
Plus the integral from, would be 3 to x
3 to x.
of ft
Uh-huh.
dt.
What do we think? Agree with that? You're shaking your head back there. Tell me. Why not? Why?
Because h of 3 is area from 0 to 3.
Okay. So what he's saying is h of 3 is already all the area, accumulated area from 1 all the way to 3. So adding h of 2 would kind of like add the green area twice. So do you agree with that? You change your mind? Okay, is that what you guys were saying too? All right, good. But this was a great idea. Good job. But yeah, h of 3 then is all the accumulated area up to 3. And now we're back to our signed area function, knowing that greater than 3, the function is positive. So we can just use the signed area, and that also gives us area, right? Okay, any questions on this? Right, so if, to say again, if you truly want an area function and your original function is dipping below, well, that takes more work, right? It takes a lot more work to get a true area function because just integrating the function gives the signed area where it decreases when that function is negative. The signed area decreases whenever the curve dips below. So you have to kind of work harder to get a true area function that always increases and tells you how much area has accumulated. All right, we're kind of done with area, and so that, like I said, I'm going to post the next the online homework will have to do with that area. Okay, get some practice on that stuff. Let's talk about the next thing, which is we're going to talk about how we can use our accumulation functions for do accumulation of volume. Okay, how do we use our accumulation functions for accumulation of volume? Here's the gist behind that. So what we're going to do to do accumulation of volume is here's the game plan. We're going to start with a curve. This is sine x. Here's our x-axis and our y-axis. Sine x from 0 to pi. And what we're going to do is I'm actually going to take that curve and I'm going to rotate it around the x-axis. And so then this brings the third dimension into play, right? So now we're actually stepping out of the plane and allowing for a third dimension in and out of the screen. And so I'm going to take that curve, I'm going to rotate it around the x-axis. Can you imagine that? And when I do that, so then all those points on the curve, I'm going to let them leave a trail and sweep out a surface, okay? And so then that surface is going to create a shell, an empty shell. Can you imagine what that empty shell is going to look like? Okay, you said yeah. Like what? Someone said a football. It's going to look like a football? Yeah, football's a pretty good description of that. An egg that's got points at the end or something like that. So, see that? All right, and so we're gonna sweep that curve around, let all those points leave a trail, and that forms what we're gonna call an empty shell. Nothing inside, just an empty shell. And then what we're gonna do is we're gonna fill that shell. We're gonna one interval at a time. We're gonna chop it up into intervals, and we're gonna fill each interval. Is going to have we're going to fill the intervals with cylinders, solid cylinders. And so those solid cylinders are going to, one by one, interval by interval, fill up the empty shell. And then we're going to track the volume of the net accumulated volume of the cylinders as they fill up the shell. So then if we want the volume of the whole thing, we'll just take our function value at the end. But we'll have a function for filling up that empty shell with what we call cylinders. This is the game plan, all right? So another example of this. Same curve, I could also rotate it about the y-axis and let it form an empty shell. What will that look like when we form a shell out of sweeping out those points? Not really a bowl. Not really a donut. Kind of, maybe there's been a donut that's looked like that in the world. A lava cake. There we go. Okay. Same thing. So when I rotate that curve around the y-axis, I get a totally different shell, but it's still an empty shell. We're going to fill that up with cylinders. And we're going to keep track of the accumulated volume of those cylinders as they fill it up. And then when it gets all the way filled up, that total accumulated volume will be the volume of the whole volume inside the shell. Okay, so that's kind of what we're doing. So we have to talk about cylinders. What is a cylinder? So So don't write on your sheet yet. You're gonna draw your own cylinders. I'm gonna draw some here. So a cylinder, you can start with any shape. You can start with any base shape. So I got like a trapezoid there. So imagine that's horizontal, and then you're gonna take that base shape and just extend it, just let it extend through the direction perpendicular to the plane. So this isn't a plane. If you just extend that perpendicular to the plane of that shape and don't alter it, keep that base shape the same. Something like that. So you're going to draw your own. Don't try to copy mine. So no matter how I slice that thing, I always get the same base shape. Does that make sense? I'm going to get that same base shape here and here and here. Every level of it is going to be the same base shape. Okay, you may think of a cylinder as like this kind of cylinder. Well, what you've thought of as a cylinder is just one variety of cylinder called a circular cylinder. Okay, so now the base, I put the base up on its end, and so then perpendicular to the base is to the right, and so I just extend that circle out to the right, and that makes a right circular cylinder. Okay, so it can be any shape. So I can do like a triangle, and then it could have a hole in it. These are all cylinders. As long as you maintain the same shape throughout the length of it, perpendicular to the base, and it maintains that same shape, then it's a cylinder. Okay, so draw one or two, make up your own. So you just make up any base shape, and then just have it be the same base shape from bottom to top or from left to right, whatever it is. If you're not a good artist, it's okay. We just need to get the gist of it. All right, so why don't you show the person next to you, and for that person to tell you if they think it's right or not. All right, so show someone, and then try to catch your neighbor with maybe with a problem in their cylinder.
Your holes are fun. Like when you do that, you have to kind of show that the micros is
Okay. Are these cylinders? Are these cylinders? Do they fit the criteria? Yeah. So the base is like the yellow. The yellow ring is like the base, and you get that same base at every height, right? So that yellow, that yellow is extended through, then it creates this cylinder, okay? So when I talked about that we're going to create an empty shell and we're going to fill it with cylinders, we're not going to fill it with all your creative cylinders that you drew. We're going to fill it with these cylinders, okay? So we're always going to fill our empty shells with cylinders that look like this. But as we're in a current interval, there's two different things that could happen to that cylinder as it varies. So it can vary this way. Its height can vary in the current interval, or its radius could vary in the current interval. So we're always going to start with this kind of cylinder, but in some situations, in the current interval, the height will vary. And in some situations, in the current interval, the radius will vary. And those are the two situations that we'll have when we're filling these empty shells with cylinders to track the accumulation of volume, right? So we're going to be accumulating volumes of these cylinders as they fill up the shell as a way of accumulating, tracking the volume in the shell. So we're going to start by looking at this one. So the one where the height changes. So if you flip your page over, let's see, do this. And while I'm rearranging my things here, go ahead and you can just read that. Okay, so I got the cylinder. Okay, so we've got our cylinder there. And you've got the dimensions, inner radius 2.5, outer radius 3, and height 7. The first thing we want to do is write the volume of that static cylinder with those dimensions, right? So we're going to write an expression for the volume of that right circular cylinder. And so what will the overall structure of that volume, how, just not getting into the details, but the overall structure of that volume that you calculate, how will you approach that? How will you do that? Yeah.
Just do like pi r squared times your height minus your pi r squared times your height again.
So a minus, so one thing minus another. So what's the first thing represent? The volume of what? Yeah, so it'd be like the volume of a solid cylinder of the larger radius, right? Like if that whole thing was filled in, you need the volume of the cylinder with radius 3, and then minus the missing piece, right? So it's going to be missing the volume, minus the volume of a cylinder with radius 2.5. Okay, see if you can write it out. Write out the volume if you haven't already.
Plus your
Okay, so now I ask, how much does did you get this? This is what I wrote it down. Check your work. Agree with that? So now that's the volume of one particular cylinder, that whole thing. Okay, so how much does the volume change? Okay, what symbols do we have for that? How would we represent, much does the volume change? dV, right? So this is asking for dV. If the height increased by 0.4 meters, we'll just do the 0.4 meters. So 0.4 meters is a dH, right? So if dH equals 0.4, if dH equals 0.4, then dV equals what? Can you write it out? Write out how much the volume varies if the height of this cylinder increased by 0.4. Go. So you weren't supposed to notice me writing, and you're supposed to be hard at work. Do you agree with that? So when you look at what I wrote, see if you agree. What did I do? I basically went final volume, which is with the new height of 7.4 or 7 plus 0.4, minus what you had before. And that will give you how much the volume changed. Agree with that? Anyone do it a different way? There's a shorter way to do it. Can't we just find the volume of the new little cylinder that grew out of this one? What's the height of that? 0.4. So I could do pi times 3 squared times 0.4 minus 2.5 squared times Does that make sense? So imagine this growing by 0.4. With that, just imagine the new little cylinder with a height of 0.4. That's how much it increased by. So that's another way. Both are important. Both are important. We'll see next time. Okay, but these are equal. This is two different ways to do the same thing. We can take the final volume minus the initial volume, or we can just notice that that change in volume was just another little cylinder sticking up on the top with a height of 0.4. Yes? Oh, yes? Okay. So look for next assignment I'll put up in the next couple hours for online homework. If I lost you at the end, come up and ask me. Come up and ask me if I lost you. Yeah. What's that? Yeah, but just pretend you didn't learn that. Yes, it's something like that.
I want to tell you, I just shouted my name, I didn't say
Okay,
here.
all right.
So, and then also, like, I want to like that, and then plus, what you were saying here, so you're saying that this equals this, correct?
Yep. Which way did you do it?
I wrote these, and it makes sense, but then I don't understand why this and this one equals, because you still have the 7 that you started with. It's not like, I guess
So
this
it's not, yeah, so when it changes by 0.4, I'll draw it in red. So when it changes by 0.4, the whole thing just gets a little taller, right? So it's like we got another one. It's like we got another little cylinder that has a height of 0.4. So it increased by 0.4. So we could just write, instead of writing final minus initial, we could just write the volume of the red one. The volume of the red one is just like this, just like a cylinder, but instead of a height of 7, its height is 0.4.
But because the question's asking how much did it increase by,
by.
I guess, because you're adding that, wouldn't it just be this, not this? This was
Both. It's two different ways to think about it. You can think about it as final volume minus initial volume, but you can also think about it, how much did it increase by? It increased by this little red cylinder. Well, that's just a cylinder by itself.
Yeah.
So you can do pi r squared h, where h is 0.4. So it's two different ways to think about it. They're equal. Is it better?